Okay, in this chapter, we'll talk about various elements and their characteristics, the periodic table, and how you're able to read the periodic table, and we'll start off with chemical symbols. Now, chemical symbols are used to represent the names of that element. The symbol will have either one or two letters. If it's one letter, you will use a capital letter. If you use two letters, only the first letter is capitalized. And here are some common examples here. For carbon, capital letter C, nitrogen, capital N, fluorine, capital F, and oxygen, capital O. For some two-letter symbols, cobalt, CO, only the C is capitalized, the O is not. Calcium, Ca, aluminum, Al, magnesium, Mg. Some very common examples of both one and two-letter symbols used for various elements. There's a table of some common elements. Some have one letter, some have two. And some of these symbols are fairly obvious what they represent. O for oxygen, C for carbon, H for hydrogen. But some symbols are completely different than what their element's name is. And that's because their symbol is based on the element's Latin name. Say, for example, copper. You would think it'd be Co, but Co is cobalt. The Latin name for copper is cuprum, so the symbol would be Cu. Gold, the Latin name for gold is aurum, so the symbol is Au, not G or Go. Mercury, its chemical symbol is Hg. Iron, Latin name is ferrum, so it would be Fe. Lead, Pb, based on the Latin name plumbum. And potassium would be P, is going to be K, because its Latin name is kalium. So some of these symbols are pretty straightforward, but some are not. So some you just have to learn to recognize. All right, now we'll move on to the periodic table. The periodic table organizes the 118 known elements into groups based on their characteristics. Just by a first glance at the periodic table, it looks like the elements are put there at random, but there's a reason why the elements are where they are. There's a reason why carbon is here and not over here. There's a reason why every single element is in the position that it is. And the learning goal for this chapter, or for this section, using the periodic table to identify the group and the period of an element, and to be able to identify the element as either a metal or a nonmetal or a metalloid. All right, first we'll talk about how to distinguish between groups and periods. In a periodic table you have rows of elements, then you have vertical columns of elements. The vertical columns are known as groups, and then the horizontal rows are called periods, and they're labeled from the top of the table down, so 1 through 7. So here's a common image of a periodic table. Period 1, period 2 goes all the way across here. Period 3, 4, 5, 6, 7, and so on. And you'll see this represented a lot this way. If you look closely at these numbers here, how it jumps from 57 up to 72, and on the row down here from 89 to 104. These two rows of elements belong in here. They're just taken out to save space. So that's how it's commonly represented with the periodic table. But these two rows actually will fit into here. Alright, the group numbers are written one of two different ways. Either numerically 1 through 18, or using a letter A or B. The letter A is used for representative elements, and then the letter B for transition elements, the ones on the bottom, the ones in the middle part where it dips down. These are transition elements. So we'll use both writing systems here since both are used. All right, here's a common example. Group number 2, or 2A, that vertical column here. And then period number 4, because that's the fourth row. 1, 2, 3, 4. So all of these have some common traits, and all of these have some common traits. All right, we'll start with the representative elements. Ones on the far left-hand side, columns 1 and 2. Then we'll jump over to the far right side. All right, the first group we'll talk about is group number 1, or 1A, depending on what system you use. These are called the alkali metals. And these will include lithium, or Li, sodium, Na, not S or SO for sodium, but its Latin name is natrium, so that's why the chemical symbol for sodium is Na. Potassium, K, rubidium, Rb, and cesium, Cs. And here are some pictures of some of those. We have lithium on top, sodium here, and potassium here. All of those are in that vertical column, that group number 1. All right, next we'll move on to group number 2, or 2A, depending on what system that you are using. These are the alkaline earth metals. These are very shiny metals, but they're not as reactive as the ones from group 1. Group 1 elements are really, really reactive. So the ones that are found in group 2, beryllium, or Be, magnesium, Mg, calcium, Ca, strontium, Sr, barium, Ba, and radium, Ra. And that vertical column, number 2. And in the picture here, strontium is what gives fireworks that bright red color. Alright, now we'll move on to the far right-hand side of the periodic table, going on to group 17, or group 7A, again based on what system you use. These are the halogens. These include fluorine, represented by a capital F, chlorine, Cl, bromine, Br, and iodine, this is a capital I. Here's some images of those. These tend to be also very reactive, just like the ones in column 1, or group 1. Alright, when you see the periodic table, it's often to see it color coordinated based on elements and their characteristics. A common way to represent that is with metals and nonmetals. So for this example here, you'll see a very thick jagged line that goes down like a stairwell here. Everything that's on the left-hand side of this, in this light blue color, are metals. Everything that's to the right-hand side of that line, this light beige, light yellow color, are nonmetals. And the elements that border this zigzag line have characteristics of both metals and nonmetals. They're called metalloids. Metals, nonmetals, and kind of a mix of both metalloids. That's why these are in like a light mint green color. Alright, we'll talk about some traits of the three of those, the metals and metalloids and nonmetals. Metals, other than hydrogen, are located on the left-hand side of the periodic table. They are going to be very shiny and very ductile, which means they're able to be bent and twisted into various shapes. These are going to be very good conductors of electricity and heat. Okay. All metals are also going to be solid except for mercury. Mercury is the only example of a metal that is liquid at room temperature. If you've ever been to the doctor and had your blood pressure taken by a manual blood pressure cuff, where the measurement is on the side on the wall, that silver liquid that goes up and down to measure your blood pressure, that is mercury inside. That's why blood pressure is measured in millimeters of mercury. Nonmetals will be on the right-hand side of the table. These are going to be very brittle and very dull, and very poor conductors of heat and electricity, but very good insulators. And nonmetals also have very low densities and very low melting points. Now the ones that kind of overlap between metals and nonmetals are called metalloids. These have properties of both metals and nonmetals. They are better conductors than nonmetals, but not as good as metals. Because of this, they're used as semiconductors and insulators, because they can be modified to function as either a conductor or an insulator. Alright, now move on to the atom. The atom is the smallest particle of an element that retains the characteristics of that element. So all elements are made up of atoms. Everything is made up of atoms. So for example, aluminum foil will have atoms of just aluminum. There are some main particles that make up the atom, and there are particles that are smaller than these that we'll mention, but we'll talk about the three principal components of the atom. They will vary in their location and their electrical charge. The first one, protons, these have a positive charge. So P for proton, P for positive. Neutrons have a neutral or no charge. So N for neutral, N for neutron. And the third one, the electron, these have a negative charge. And you'll see on the images over here, charges that are similar will repel each other, and charges that are different will attract each other. Just like if you play with magnets, if you put two of the same pole next to each other, they repel each other. They cannot stick together. There's no way you can force them to stick together. But if you have opposite poles on a magnet, they combine and they attract each other. It's the same thing here. So two positive charges will repel each other the same way as two negative charges would. So like signs repel and opposites attract. So positive, negative, negative, positive. Alright, the structure of the atom. The atom is made up of a nucleus, which is the key center point of the atom. This is where you'll find the protons and the neutrons of an element. It has most of the mass of that atom will be found in the nucleus. And the third particle we talked about, the electrons, actually orbit the nucleus, kind of like the planets orbit the sun, in various shells or various orbitals. And for the most part, that area is a lot of empty space. Alright, so it's starting with a sample of lithium metal here, zooming in on these little individual circles, these individual lithium atoms. So zooming in even closer, going into the one atom here, and the nucleus would be here. These would be electrons orbiting around here, swirling around. Then the size of the nucleus of a lithium atom is approximately 10 to the negative 15 meters. So an incredibly small amount of space. And again, when you're talking about one atom, the high majority of the space occupied by an atom is done by the nucleus, where you find protons and neutrons. Alright, now we'll move on to how to read various characteristics of the periodic table and with any given element. When you zoom in on the periodic table, you'll see these individual squares, and within these squares you'll see the element's symbol, and you'll see some various numbers, and we'll talk about what all those numbers mean. The first one is it's called the atomic number. This is always going to be a whole number. It's going to be specific for that element. So these are put in sequential order. 1, 2, 3, 4, going all the way up to 118. They're always going to be whole numbers. And this atomic number represents the number of protons and electrons in an atom. And it usually will appear just above the symbol for the element. So for the example that's given here, Na, the symbol for sodium, its atomic number is 11. So that means right away, just by looking at this individual square, of the three particles that we talked about, you know right now how many protons there are and how many electrons there are in a neutral sodium atom. There'll be 11. Right, for neutral atoms, the net charge will be 0. So that means the number of positively charged protons equals the number of negatively charged electrons. They cancel each other out. So some atoms are neutral, and then some are going to be more reactive and they want to lose or gain electrons. And when that happens, their charges will change. And we will talk about that in a future chapter. So the example that's given here, aluminum, its atomic number is 13. So that means it has 13 protons, which are positive, and 13 electrons, which are negative. So they cancel each other out. A net charge of 0. All right, the mass number, or the atomic mass units, AMU, this represents the number of particles within the nucleus of an element. Now this is equal to the number of protons plus the number of neutrons. This is always going to be a whole number. You can't have a third of a particle or a tenth of a particle. This is always going to be represented by a whole number. And this is a number that does not appear on a periodic table. This is used for calculations for other formulas, but it does not appear on the periodic table along with the chemical symbol. All right, now we'll talk about isotopes. Isotopes are atoms of the same element, but they have different mass numbers. And the reason why they have a different mass number is their mass is different because there are a different number of neutrons in that version of the element. An isotope is really just a different version of that element. Most elements can be or can exist in more than one form. And a way to recognize if an element is an isotope or not is the way that it is written. The example that's given here is magnesium. The normal way you would write or you would represent magnesium is just the symbol Mg. But when you see the symbol here, along with the mass number and the atomic number, along with that symbol, that means that it's an isotope. The atomic symbols being able to determine subatomic particles. We've already talked about how to find two of the three subatomic particles, the protons and electrons. That's given by the atomic number. To find the number of neutrons, what you do is you subtract the atomic number from the mass number. And here are some examples. Let's go down here to zinc. Chemical symbol is Zn, zinc. Mass 65, and the atomic number is 30. This number here, 30, represents protons and electrons. The mass is 65. So 65 minus 30 gives you 35 neutrons. And this is the same process done for any element on the periodic table, regardless if you have heard of it or not. The atomic number always represents protons and electrons. And to find neutrons, you subtract that number from the atomic mass and then round to a whole number. Because you cannot have a tenth of a neutron or a fifth of a neutron. So same thing here for phosphorus. Atomic number 15. So 15 protons and electrons, even though it's not listed on the table here. The mass is 31. So 31 minus that 15 will give you 16 neutrons. Sometimes there's only a very small number difference, 1 to 2. Sometimes there's a very big difference between neutrons and the other particles. All right, ways to calculate atomic mass. If you look at the periodic table, you will see usually the chemical symbol, like for here, chlorine, Cl, the atomic number on top, 17. And you also see a number below the atomic symbol, and it's almost always a number with a decimal in it. So for this example, 35.45. And this represents the average weight of all the naturally occurring isotopes of that element. So for chlorine, it is found naturally to exist in two forms, either with a mass of 35, here, or a mass of 37. It is still chlorine, that's why the atomic number doesn't change. They're both 17, so it's still chlorine, but the masses are different. So that's why they're isotopes. So there's a way to calculate the average mass, which is what this number represents. So for the example here for chlorine, 75%, or just over 75%, of all the naturally occurring chlorine has a mass of 35. The other 24% has a mass of 37. So when you average this out mathematically, you get the average atomic mass of 35.45 atomic mass units, which is how we get this value here. All right, to calculate atomic mass, what you'll do is you will multiply the mass of that isotope by its percentage, how abundant it is, and then you will do that for every single isotope. Then you will add up all those numbers together to get the average atomic mass. All right, this table here shows the three different naturally occurring isotopes of magnesium. Magnesium 24, 25, and 26. And the masses of those isotopes. So the mass for magnesium 24 is 23.99. Officially 24.99, 25.98. The most abundant, the most commonly occurring of these three isotopes is this one here, magnesium 24. That is found 78.7% of the time. All right, so what you'll do is you'll take the percentages that you're given, turn that into a decimal number. So this becomes 0.7870. That value multiplied by the mass that you're given, that will give you 18.88 atomic mass units for that isotope, for that version of magnesium. You do the same thing for all the other known isotopes. Magnesium 25 is found 10.13% of the time. That converted into a decimal number multiplied by the mass, you get 2.531 atomic mass units. And this last version here for magnesium 26, which occurs just over 11% of the time, 11.17. Convert that into a decimal. That value times 25.98, its mass, gives you 2.902. Adding up all of these three together, 18.88 plus 2.531 plus 2.902 gives you the atomic mass unit for magnesium, which would be 24.31, which is the value that you will see on the periodic table under magnesium. And it's the same process for any other element with any number of isotopes. How abundant it is multiplied by its mass, and you add up all those atomic mass units for every single isotope that's known. Alright, next we'll move on to electromagnetic radiation. Now we experience electromagnetic radiation every day, all the time, in various forms. X-rays at a doctor's office, seeing the colors of a rainbow, seeing light, talking on your cell phone. Those are all examples of electromagnetic radiation. Now this radiation will consist of energy particles that move as waves of energy. So think of a wave going up, then going back down. There's the top part, which is the crest or the peak, then it dips down into a trough. So the distance between these peaks of these waves, think of waves occurring at an ocean, the distance between those tops of those waves is called the wavelength. Radiation that has high energy will have much shorter wavelengths, and radiation that has low energy has much longer wavelengths. So if you were to think of a wave going like this, right there is the peak here. And then down here will be the trough as it dips down. And distance between here and here will be the wavelength. Radiation that has higher energy will have much shorter wavelengths. These will be much closer together. A radiation that has low energy, these will be much further apart. So it may look like this. That would be low energy, and this would be high energy. Okay, now we'll move on to the atomic spectrum. When light from a heated element passes through a prism, it will separate into distinct colors of the rainbow. Any light going through a prism will separate into the standard rainbow colors. But whenever you do that with an element, you'll get a very distinct pattern that's unique for that element. So the example that's given here, if you were to heat up barium and heat an element, that light going through a prism will split up into this pattern. This is unique for barium. If you were to do this with calcium, you would get something different. Or potassium, you would get something different. Every element has a very unique atomic spectrum like this. Alright, here's the full range of the electromagnetic spectrum. Starting off here, very low energy. Here. And then getting higher and higher and higher to high energy. Now the part of this whole spectrum that we can see, visible light, is a very, very, very small piece of the spectrum, going from here to here. Now the color is red, about 700 nanometers. That's going to be on the lower end of the visible light. Then the various colors of the rainbow. And up here you get violet at around 400 nanometers. That's why anything below red is infrared. Anything that's above violet is ultraviolet. So some examples here of infrared light, from heating lamp, satellite, microwaves, cell phones, TV, and so on. And things that are ultraviolet, just beyond violet. These are getting higher and higher in energy, which means more dangerous to deal with. X-rays, gamma rays, and so on. That's why when you're getting an X-ray, the part of you that's not being X-rayed, you need to have a shield of lead in front of that, otherwise it can damage tissue. And again, this whole spectrum, which covers quite a lot, the only part that's visible to us is this small window of the rainbow colors, from 700 nanometers to 400 nanometers. Now we'll move on to electrons and energy levels. Now electrons, like we mentioned before, exist in different shells or different orbitals that spin around the nucleus. Electrons with the same amount of energy are grouped in the same energy level. And energy levels are given what are called principal quantum numbers, or the N number. So N1 is the lowest, then the next higher level will be N2, and 3, 4, and so on. So think of them as like this picture indicates, like a bookshelf. The lowest level, or N1, then the level just above that, we have a little bit more energy, N2, and more energy, you have N3, and 4, and 5, and so on. An electron can only exist in one level at a time. Now when electrons move up or move down energy levels, energy will either be absorbed or emitted. So an electron will go to a higher energy level when they have absorbed enough energy to push them up to the next level. So if you have an electron here, and it collects and absorbs a whole bunch of energy, it gets bumped up from, say, N1 to N2, or 2 to 3, and so on. If you move up to more than one level at a time, that means the electron has absorbed a lot of energy. So it will go from, say, here all the way up to here. And then the opposite of this will be true. If an electron goes down in energy level, let's say from N3 to N2, as it falls back down, it will emit energy that's equal to the difference between those two levels. So energy is never gained or lost. It's always there somewhere. If it gets absorbed, it pushes the electron up to a new level. If the electron falls down in energy level, the energy that is the difference between those two levels gets emitted as light. Now it is the arrangement of these electrons that helps determine chemical and physical properties of any given element. And each energy level, N1, 2, 3, 4, 5, and so on, has one or more sublevels. And the number of these sublevels within an energy level is equal to the quantum number of that level. And the sublevels are identified by these letters S, P, D, and F. And these are the order that they go in. So S would be the lowest sublevel. Then a little bit more energy, you get P. After P, you get D. After D, you get F. A quick resource to summarize the energy level with the principal number of sublevels and how they're written. And we'll talk about what these boxes represent here in a second. So the lowest energy level, N1, has one sublevel because it's N1. So it'll have one box in the S sublevel. Quantum number 2, because it's a number 2, it has two sublevels, S and P. Energy level number 3, you have three sublevels, S, P, and D. And for 4, you have four sublevels, S, P, D, F. And these individual boxes have a very particular meaning, which we'll talk about here soon. Now the location of where an electron is, to what sublevel it's in, really is determined by probability. An electron can't exist in, as far as we know, can't exist in two different places at the same time. So you are predicting where it was or where it will be. Now we'll first start talking about the lowest energy levels, the S sublevels. These are three-dimensional volumes where electrons have the highest probability of being found because it's the lowest energy level. And when you're talking about these on paper, they're usually indicated by three-dimensional spheres like this, because electrons can move in three different dimensions. So think of it as like a baseball or a tennis ball, because the electron could be swimming around anywhere in there. All right, the P suborbital levels. There are three of those, starting with the N number of 2. Each P orbital has two lobes. Think of it as a long, skinny balloon that's kind of pinched off in the middle. So you have two oblong sections that are joined together. And each of these lobes can hold 2 electrons at the most. And the 3 P orbitals are arranged perpendicular to each other on an X, Y, and Z axis around the nucleus. And in what direction an electron spins, either counterclockwise or clockwise, will give it different properties as well. Images of how a P orbital would look: a long, skinny, in this case, green balloon that's kind of pinched off in the middle. Same thing here, same thing here. And then we have the combined P orbitals that look kind of like this, all perpendicular to one another. This image is a combination of these three together. The next one, the D orbitals. Each of these D sublevels have 5 D orbitals. For the most part, they have a fairly consistent arrangement, except for this last one. The first 4 of these 5 are aligned with each other, very similar to the P orbitals. But this last one has a circular orbital, looks kind of like a donut that encloses the other orbital here. So all of these indicate the D suborbital level. In this table, you have the electron capacity for these energy levels going from 1 to 4. They're starting off here in the bottom. The lowest energy level of N1 that has one sublevel. That's indicated by writing 1s, because there's one suborbital level in the S range. For N level 2, that means 2 sublevels. So you're going to write 2s and then 2p also. This one the S's can only hold 1. P's can hold up to 3. N level of 3. That means you have 3 sublevels. That's why these numbers are the same as the quantum number. So these numbers are the same as this. So 3s, and then 3p, and 3d. It's always in the same sequential order. It's always S, then always P as in Paul, and then D as in David, and then F. Again, S can only hold 1, P can hold up to 3, and then D holds up to 5. And lastly, for number 4, again, the numbers are all the same: 4s, 4p, 4d, 4f. And each of these contain a set number of electrons, and that's very important, because where these electrons are in these suborbital levels will determine if they are lost or if they're gained, or do they move down levels or do they move up levels to make a element more stable. So these orbitals have very consistent, very predictable patterns. The first one can only hold 2. Then the next level can only hold 8. Then it goes up to 18, then up to 32. These electron configurations follow the order of occupied sublevels on the periodic table. Again, by looking at the table, just by knowing some basic facts about chemistry and knowing what to look for, you can tell a lot of characteristics of any element just by where it's placed on that table. So all these in the S block here, we'll have all just 1. Then the D block here, P, and then F. Now what's used to indicate these electrons and where they're placed in what orbital level is what's called an orbital diagram. Now these orbitals will be filled based on energy level, going from the lowest to the highest. The lowest energy levels are always filled up first, and then when those energy levels are filled up, then you move on to the next level. So in this example here, each arrow indicates one electron. And remember here, S's are the lowest kind. So the S's will be filled up first before anything gets put in the P level. After the P's are filled up, then you move on to the next one. So you're not going to go some here and then some here, some here. The lowest energy levels are always completely filled first before you can move on to the next. Now chemists will use a particular type of notation called electron configuration to not only indicate the placement of electrons in the atom, but to show how electrons fill various energy levels and sublevels. And there's an abbreviated form using a particular noble gas to represent all the electrons preceding it. That's a shorthand way to write an agreed upon setting for all these configurations. So for an example, the electron configuration for carbon, when you write it out using this type of setup, and we'll go over an example of one here in a second also. Carbon, it'd be written just like this, and this is how it's read: 1s2, 2s2, 2p2. And here's what those numbers mean. 1, or the very first suborbital level, 1s, and there are 2 electrons there, so that means it's full. The next level will be 2, 2s, and it has 2 electrons, so that's full. Then after that you go up to the next level, which are p's, 2p, and 2 electrons in there. And here's how you would write some other common elements. Helium, H, atomic number only 1. So it's only going to be 1 electron. So you only fill in just half of the very first box. So that'd be written as just 1s1, because there's only 1 electron in this box. For helium, atomic number 2, the lowest box is full, so it's going to be 1s2, because there are 2 here. Alright, here are some other common ones. On period number 2, from lithium down to neon, the way it's the element and the atomic number, the orbital diagram, note the boxes, the electron configuration here, and also how it is abbreviated, an abbreviated electron configuration. And here's what that means. For this last column, you'll see helium in brackets and plus whatever's left over, because this is the same thing as this, 1s2. So you could also write this as 1s2 and then the rest. Instead of writing all of that, you just write helium in brackets. So that's a shorthand way to write 1s2. That's why it appears in all of these. So it's not mandatory you write it that way, but it's an abbreviated form to write the electron configuration. Alright, we talked about carbon previously, atomic number 6, and how these 2 are full, these 2 are full, and these are not. And the name that we get, 1s2, 2s2, 2p2. And this is how we get to these arrows getting placed where they are. Alright, what we have here are the orbital diagrams for carbon. And I've already written out here 1s2, 2s2. All 3 of these are 2p2. And like I mentioned, when you're filling out these boxes, filling out these orbitals, you always want to fill out the lowest energy levels first. So for this one, for carbon, you have 1 arrow here, 1 arrow here. You want to fill that box up first because it's the first level, it's 1. Then 2, that would be full. That would be full. So there's 2 here, 2 here. Alright, carbon will have 6 electrons. So right now we have 4. We have 2 in here, we have 2 in here. So now we start to fill out these. 1 there, 1 there. You would not put it here. You would go here, this box next, and then fill the rest back in. So that's how we get 2, 2, 2. That's how we get to our 6 electrons for carbon. That, what I just drew by hand, is the same thing as this, just nowhere near as neat. 1s2, 2s2, 2p2, because there's only 2 here. If you look at the difference between carbon and nitrogen, this one is filled up here, or this box on the end does have an electron here, but not here. That's why nitrogen is almost the same thing, but it's 2p3, because there are 3 here. Again, the key for all this, when you're writing an orbital diagram, you fill out S level first and then go on to P. After P, then you fill in D. After D, then you go to F. The lower levels are always filled up first before you even move on to the next. All right, for representative elements in groups 1 to 18, chemical properties are due to what are called the valence electrons. Valence electrons are the electrons on the outermost energy level for that element. These are how elements combine with each other. Some electrons are going to be lost to make that element more stable. Some electrons will be gained to make that element more stable. And the group number that the element is in gives you the number of valence electrons for that element. Just knowing what the group number is can tell you right away without having to draw the orbital diagrams how many electrons there would be in the outermost shell and how many they are able to be lost or to be gained. For an element to lose one of its outermost electrons, that takes a certain type of energy. And that energy is called ionization energy. The energy needed to form an ion. An ion is an element that has a charge to it. So it's the energy needed to basically rip away the outermost electron and therefore leaving an ion behind. So the example that's given here, sodium plus the ionization energy will give you the sodium ion, Na+, and the negatively charged electron. This is the same thing as this, but written in orbital diagrams. This right here is all for sodium. And what the ionization energy would be is the energy it would take to rip away this electron here. That's why in the product part of the equation here, this box is now empty. And the arrow is here on the outside. So that's all the ionization energy is. The energy that's required to form the ion. And by doing so, pulling away the valence electron or electron. Now, as the distance from the nucleus to the valence electrons goes higher, the ionization energy will go down. It takes less and less energy to pull something that's further away from the nucleus. If it's really, really close to the nucleus, it's going to take a lot of energy to pull it away. And this ionization energy will be low for metals, but high for the non-metal. All right, here's a quick way to just look at the periodic table and to get an idea of what ionization energy would be needed. The energy will decrease when you go down a group and increase as you go across, going from left to right. So a generic image of the periodic table here. When you go down, the ionization energy will get less and less. So something down here would not take as much ionization energy than something up here would. Also, as you go from left to right, going this way, the amount of energy will increase. So something that's, say, in this corner here, where the cursor is, will take a high amount of ionization energy compared to something down here. So going down, the energy needed decreases, and going to the right, the energy increases. And here's another way to think about it. We have three examples given here: lithium, sodium, and potassium. Of these three, lithium is smaller, or the smallest of the three. And sodium is a little bit bigger, and then potassium is a little bit bigger than that. So the distance between the nucleus and its outermost shell is really small here, a little bit bigger here, and a little bit bigger here. The energy you would need to take away this electron would be less than here and less than here. This is really, really close to the nucleus. So pulling away this lithium electron would take a lot more energy than it would compared to potassium, because that's further away. Not that much, a little bit more, a lot more. All due to its distance between the electron and the nucleus. Closer it is, more energy you need. Alright, an element with a metallic character is one that loses a valence electron fairly easily. And these are going to be more found or more prevalent in metals on the left-hand side of the table. It's less for non-metals on the right-hand side because they don't lose electrons all that easily. And this character will decrease going down a group as electrons are further away from the nucleus. So again, given a generic image of the periodic table, as you go down the table, the character will increase. As you go to the right, the metallic character will decrease. And the reason why that is, and it's something that we'll discuss further in a future chapter, the elements that are on this hand side of the table, especially column 1 and column 2, are really, really reactive. They are very willing to give up that valence electron. They are much more stable when they lose that 1 or 2 on the outermost shell. They want to get rid of them as quickly as they can. And the opposite is true over here. See in column number 17, fluorine, iodine, chlorine, all those. They are much more stable to gain an electron. They don't want to lose the ones on their outermost shell, because for them to become more stable, it's easier to gain one than it will be to lose the ones that they currently have. So that's why the elements on this side of the table much more eager to lose their valence electrons, because by doing so they become much more stable.
Thank you for watching our newest video on our crash course in chemistry. We'll have new videos in this lecture series every Monday and every Friday of each week. So stay tuned for our next video in a few days. And don't forget to subscribe to this channel so you can be notified of when our new videos are posted each week.